fix once and for all, and F embedding of k in A. So this is possible since RD has been assumed to be even. So such an embedding is unique up to G conjugacy, and denote by H the centralizer. H is the centralizer of K in G. So, since K is separable over F, we may choose an element delta in K such that K is generated by delta over F. The square of delta is an element alpha of F, which is not a square in F. And this element alpha is a well-defined mod the squares of F times. And once delta is fixed, then H is the subgroup of G made of the points of G which are invariant under the involution tau, which is conjugacy by delta. So tau is the inner involution which appears in the title. So now say that I will consider irreducible smooth complex representation of G. So an irreducible representation of G is said to be H distinguished or just distinguished for simplicity. H distinguished if the vector space H, so call it pi C is non-zero. So that is if the vector space of V carries a non-zero linear form, which is invariant by the subgroup H. So we are interested in the classification, in the characterizations of those irreducible representations of G, which are distinguished by H. And we'll see that it can be done in terms of the Langlands parameter. So more precisely, there is a conjecture. There is the following. There is a following conjecture which has been stated by Dipendra Prasad and Takloo-Bighash. In 2011, I think, so which is as follows. Let pi be an irreducible representation of G, and let phi be its Langlands parameter. And so the conjecture has two parts. First part, can you see if I write here on the top right? Okay. So first part of the conjecture, if the Jacquet-Langlands transfer of pi is generic, and if pi is H distinguished, then first, the Langlands parameter phi takes values in the symplectic group SP2N, and B, the root number epsilon at 1/2 of the restriction of phi to the veil group of K is equal to -1 to the R. So the conjecture gives you a necessary, so at least for generic representations, a necessary condition for being distinguished by H. And the second part tells you that for discrete series representation, this necessary condition is also sufficient. So part 2, if pi is essentially square integrable, then and satisfies conditions A and B, then pi is H distinguished. Okay.
Vincent, so in the case where K is contained in the, is H just GLR K?
In the case when R is contained in D, if D is quaternionic, yes, but if D is not quaternionic, it will be GLR of some division algebra over R over K. So H need not be split over K. Let me make a couple of remarks before explaining what is known about this conjecture now. So the first remark is that there is Prasad and Takloo-Bighash gave a more general conjecture about not only about distinction, but about distinction by a character. So about ohm H by mu to be non-zero for some character mu of for a given character mu of H, and second remark, which is about this assumption, genericity assumption. It has been recently observed by Miyu Suzuki that the assumption, the genericity assumption, is not necessary. Is not needed. Okay, now what is known about this conjecture? So originally the conjecture is generalizes results by Tunnel and Saito, which correspond to the case where n is equal to 1. And Prasad and Takloo-Bighash themselves gave a proof of their conjecture in the case when n is equal to 2. More recently, Feigon, Martin, and Whitehouse I think it is dated 2018, proved the part 1 of the conjecture in the split case, so when G is GL2NF, so D equals 1, and for pi cuspidal, and also assuming that F has characteristic 0. Then, more recently, Chomeau and Matringe proved part 2 of the conjecture for twist of the Steinberg representation of G. And in the split case, so D equals 1, and pi cuspidal of level 0. And I should add P different from 2. Because the same restriction on P will appear later. Then, even more recently, Hangshe proved part 1 of the conjecture when pi is essentially square integrable, and also part 2 of the conjecture when pi is cuspidal and its Jacques-Langlands transfer is also cuspidal. And in a work in progress, Miyu, Suzuki, and Hangshe prove that part 2 of the conjecture reduces to the case where P is cuspidal. So I should have said that yes. So all of these results assume that the characteristic of F is 0. Okay, now the main result I will discuss in this talk is the following. Suppose P is not 2 and the characteristic of F is 0. Then part 2 of the conjecture holds for cuspidal representations. So which was the remaining piece to be proved in this case. So if I summarize, so first, we thus have a full proof of the Prasad and Takloo-Bighash conjecture when P is odd and when F has characteristic 0. Another remark is that there is a result of Guo, which has been generalized by Broussus and Matringe, saying that if pi is irreducible and H distinguished, then its Langlands parameter phi is of symplectic type. No, sorry. No, it's not the right line. So if pi is irreducible and H distinguished, then pi is self-dual. So which is why in the remainder of this talk, I will only consider self-dual cuspidal representations. Let me make a last comment before explaining the general strategy of the main theorem. Part, the proof of the main theorem that I will present in this talk uses a weak form of the results by Hong-Xue. More precisely, it requires the following implication. If pi is cuspidal and H distinguished, then its Langlands parameter phi is of symplectic type. Okay. Now I will say more about the strategy of the proof of this result. There are basically it can be decomposed into two general parts. The first one is that it requires Bushnell-Kutzkow's theory of simple types. And the second aspect of the strategy is a counting argument.
Can you ask a quick question?
Yes.
What's the relation in view of the conjecture? Just I'm trying to unpack it. What's the relation between distinguishability for the pi and the distinguishability of the Jacquet Langlands of pi?
It is the relation. Well, it only depends on the parity of the integer r. So if you look at the condition on the Langlands parameter given by Prasad and Takloo-Bighash conjecture, you have a condition on phi itself, which has to be symplectic, and there is a root number which has to be equal to -1 to the power of r. So r is the integer such that your inner form is GLRD. So if r is even, pi will be distinguished if and only if it's a Jacquet-Langlands transfer is. And if r is even, if r is odd, it changes the distinction property. Let me say more about the.
Sorry, maybe something else. But this sign is it the same sign which occurs in the, the trace identity for the Jaquet Langlands, or is it a different sign?
The sign which occurs in the Jaquet-Langlands trace formula is -1 to the 2n minus r. So yes, it is the same sign. Yes. Does it answer your question? Okay. So let me say more about this first aspect of the strategy, so which is about type theory. So basically the idea is that any cuspidal irreducible representation of the group G has a model of the following form. So call it pi. Of the following form, pi is isomorphic to some compactly induced representation. Compact induction from J to G of some representation lambda, so which is the space of functions from J to the space of lambda, which are locally constant and compactly supported, mod J, and such that f of x g is lambda of x f g for any x in J and any g in G, where J is a certain compact mod center open subgroup of G, and where lambda is some irreducible representation of J. Such a description of cuspidal, and so such a pair J lambda is called the type. So such a description of cuspidal irreducible representations of G has been constructed by Bushnell and Kutzko in the split case. So for cuspidal representations of GLN F, and it has been extended to inner forms of GLN by several people, starting with Brousseau, Martin Graditz, Sean Stevens, and I. In a context of distinction, the idea is that if you are given such a model for your cuspidal representation, restricting pi to H gives you a decomposition as follows. Pi restricted to H decomposes as a direct sum of factors of the form. So compact induction from H intersect JG to H of lambda conjugated by G, where G ranges over the double cosets of G mod J. And if you are interested in the distinction of pi, you are restricted to, you are reduced to analyzing the contribution to distinction of each of these summands. This approach has been used, it goes back at least.
There is H on one side, right?
Is there a question?
In the double cosets, there is H on one side.
Oh, thank you. Thank you. So double cosets, yes. Thank you. So this approach goes back at least to Hakim-Nerlagan, who used this strategy for essentially tame cuspidal representations of GLNF, so where essentially tame means that the restriction of the Langlands parameter to the wild inertia subgroup decomposes into characters. Now, let me explain the second aspect of the strategy, which, as I said, is a counting argument. So if we want to make to use a counting argument, the first thing to do is to reduce, to make finite sets appear. So for that, we are going to fix an additional parameter. So we could let phi be a self-dual cuspidal representation of G, and consider so phi it's Langlands parameter, and restrict the Langlands parameter phi to PF, where PF is the wide inertia subgroup. So that is the maximal pro-P subgroup of the Weil group. And pick, so fix some irreducible component gamma, irreducible component of the restriction of phi to the wide inertia. So gamma is not unique, but it is unique up to WF conjugacy. And I will denote by big theta the WF conjugacy class of gamma, which is uniquely determined by the cuspidal representation pi. And in the sequel, I will suppose, for simplicity, that gamma is not trivial. That is, pi has positive level. This is for simplicity because in the level 0 case, the counting argument takes a slightly different form. So now, consider that this WF conjugacy class has been fixed once and for all, and consider the following set. I will denote by A of G theta the set of cuspidal self-dual representation of G with I'm going to give a name to this. This, I will call it the endoclass of pi. And so here I fix the endoclass with endoclass theta. In A, let ASP denote the subset made of cuspidal representations such that phi is of symplectic type. And in ASP, let APTB denote the subset of cuspidal representations which satisfy the conditions of the Prasad and Takloo-Bighash conjecture. So pi is in ASP, and the root number epsilon of 1/2 of the restriction of phi to WK is equal to -1 to the air. And at last, let A dist denote the subset of A made of cuspidal representations which are H distinguished. All these sets are finite. Because the endoclass has been fixed and the representations are self-dual. And the goal of the counting argument is to prove that we have the containment A dist contained in A dist contained in A PTB, and that they have the same cardinality. Okay. As I said, this containment, strictly speaking, it has already been proved by Hong Xue, who proved that the condition given by Prasad and Takloo-Bighash is a necessary condition for distinction. But I will not take this for granted. I will only use a weaker form of this containment, which is enough for me. So this is step one. So step one is my starting point. It is the following containment. I will start from the fact that A dist is contained in A SP. And I do not assume that the condition on the root number is satisfied. And so, as I said, this is due to Hong Xue. Now, step two. I will consider a self-dual cuspidal representation pi with fixed endoclass. It has a Langlands parameter phi, and for simplicity, I will denote by epsilon k of phi the root number, epsilon of 1/2 of phi, restricted to WK, times, so it is convenient to normalize it by multiplying also by the determinant of phi at -1. It makes no difference for representations of symplectic types. These determinants will be trivial anyway. But for self-dual cuspidal representation, it might not be trivial. So now consider the stabilizer of the factor gamma in WF. So remind that gamma is a fixed irreducible component of the restriction of the Langlands parameter to wild inertia. And you consider it's a stabilizer in WF. So it is of the form WT for some finite tamely ramified extension T of F. And consider also the stabilizer of the direct sum gamma plus the contragradient of gamma in WF. So gamma is an irreducible representation of a pro-P group. P is different from 2. Gamma is not the trivial character by assumption. So gamma cannot be self-dual. And so the stabilizer of this direct sum is slightly bigger than WT. It is of the form WT0, and T is quadratic over T0. And I also introduce an additional invariant. I will define the degree of theta to be the dimension of the irreducible component gamma times the degree of the extension T over F. And this is a divisor of 2n. Now I can state the following theorem. Given a self-dual cuspidal representation pi with given Endoclass, the root number epsilon k of phi takes the value -1. Sorry, one has takes the value -1 to the r if and only if first 2n over the degree of theta has the same parity as the integer r, and second part, the element alpha. I remind you that K is generated by some elements delta over F, and alpha is the square of delta, which is assumed to be in F. And the second condition is that alpha is a norm with respect to T over T0, if and only if R is even. So if you consider this theorem, if you consider conditions A and B, you can see that it only depends. It only depends on the Endoclass theta of pi. So what does it mean? It has the following consequence, corollary. The condition in the theorem only depends on the endoclass theta. Thus, there are only two possibilities. Either the condition is never satisfied, so epsilon k of phi has never the expected value, and then the set APTB is empty, or the condition is satisfied, and then epsilon k of phi always takes the expected value, and then APTB is exactly the same as ASP, which has cardinality equal to one half of the cardinality of A. Because half is of symplectic type and half is of orthogonal type. Now, let's go to step 3. Now, we need to interpret the endoclass theta on the G side. Theta has been defined on the Galois side as some WF conjugacy class of an irreducible representation of the wide inertia subgroup. But if we want to go further, we need an interpretation of theta on the inner form, on the GLN side. Step 3, interpret theta on the G side. And for this, one has to use the Bushnell-Kutzkos theory of simple characters. I will not explain what it is in detail, but I will say that first, a simple character for the group G is a character of a certain open pro-P group, pro-P subgroup of G, and its construction. Second remark: any cuspidal representation of G contains simple characters, which is related to the description of pi. So pi is my cuspidal representation as the compactly induced representation from some Bushnell-Kutzkos type. And so any cuspidal representation contains simple characters. There are infinitely many possible simple characters in a given cuspidal representation, but considering that we have self-dual cuspidal representation, it is natural to ask, does a self-dual cuspidal representation contain a specific simple character, meaning a simple character having special property with respect to the fact that the cuspidal representation is self-dual. So I'm going to be more precise. If pi is a self-dual cuspidal representation of G, it may contain a simple character denoted theta, such that theta is equal to the inverse of theta composed with the involution tau. So remind that tau is the inner involution given by a conjugacy by the element delta. And we have the following condition. A cuspidal self-dual representation pi with a given endoclass big theta contains such a simple character, which I will call a tau self-dual simple character, if and only if the two following conditions are satisfied. And you will see that it is exactly the same conditions as before. 2n over Doug, theta, and r have same parity. And second, alpha is a norm with respect to t over t0, if and only if r is even. It has two consequences. The first corollary is that, of course, a cuspidal self-dual representation contains a tau self-dual simple character if and only if the root number epsilon k of phi is equal to -1 to the r. And the second corollary is that since the condition in theorem 2 only depends on the endoclass big theta, we have the following. The following are equivalent. First, there exists a cuspidal self-dual representation of endoclass theta containing a tau self-dual simple character. It is equivalent to any cuspidal self-dual representation in A contains a tau self-dual simple character. So if one of them contains a tau self-dual simple character, all of them have this property. And third equivalent condition, the set APTB of cuspidal representations satisfying the Prasad and Takloo-Bighash condition is not empty. Now we go to step 4. Step 4, now we need to relate distinction to what we have seen in steps 2 and 3. So step 4 is the following property. Any H-distinguished cuspidal representations contains a self-dual simple character. So this is why the notion of self-dual cuspidal character is interesting. It is because it is related this way to the fact of being distinguished. And if you look at this corollary, it tells you that if there exists a distinguished cuspidal representation of given endoclass, then the corresponding set A PTB is not empty because of this. And now there is one remaining step. Last step. So we are going to finish the counting argument. Suppose that APTB is not empty, then so this corollary tells you that there exists a self-dual simple character in any pi in A. So by using a self-dual simple character and type theory, one constructs a family of 1/2 of the cardinality of A distinguished representations in a dist. And what does it tell you? You have the following inequality. So you have the set of H distinguished cuspidal representations. You know that it is contained in APTB. This one, when in the case when APTB is not empty, we have seen that this one is equal to ASP, and it has cardinality 1/2 of the cardinality of A. And this one, we have just said that its cardinality is at least 1/2 of the cardinality, 1/2 of the cardinality of A. So the containment is an equality, and it finishes the proof of the main theorem. Thank you.
Questions, please.
So maybe some knee-jerk reaction questions. So first of all, where did you use characteristic 0?
Excuse me, say it again.
Characteristic 0, what did you use it?
The only reason why I restrict to characteristic 0 is because of step 1. Because of step 1, I use the results by Hang Xue, which says that if a representation is distinguished, then its Langlands parameter is of symplectic type. And this is written only in characteristic 0.
Uses a global argument or?
Yes.
You know, another obvious question, is the multiplicity 1 in this context?
Yes, there is multiplicity 1. In the split case, or at least for cuspidal representation, in the split case, it should be due to Guo. And I think in general, in the inner form case, it is due to Broussus and Matrange, the multiplicity 1 property.
For cuspidal or in general?
In general.
And the last question, so once you have multiplicity 1, then I guess there is an involution which, I mean, there is a normalizer, I guess, for the H, non-trivial normalizer.
The normalizer of H in G, you mean?
Yes.
Yes.
And then the question is,
there is a Galois group.
What is the sign on by which it acts? Is it the same kind of sign, or is it?
What is the sign?
I mean, the non-trivial element in the normalizer, if there's multiplicity 1, it acts with the sign. So I wonder what is the sign is related to the sign that you have.
I did not think about it.
Vincent, can I ask you a question?
Yes.
This notion of endoclass has been there for a long time, no?
Yes, it is. So it is due to Bushnell and Enyart. So actually, I did not define it the right way in my talk. In principle, the endoclass is defined on the GLN side, and then it is interpreted on the Galois side. So I did the other way around.
But I'm just thinking that your use of endoclass seems to be very novel and very kind of out of the blue.
Well,
this has not been used in the counting problems so far.
For a distinction problem, you mean?
No, I'm just wondering whether the endoclass, the notion of endoclass has been put to similar use in the past. Perhaps not.
For a counting argument, you mean?
Yeah.
Yes. For instance, so with Alberto Minguez, we studied the congruence properties of the Jacquet-Langlands correspondence, the mod some prime number different from P, and in order to prove that the Jacquet-Langlands correspondence is compatible with congruences, at some point we use a counting argument which is more or less based on endoclasses.
All right. No, it looks very beautiful, very kind of interesting. Yeah, good. Nice.
Thank you.
I still couldn't understand. What is the relation between distinction and symplectic group? How does it come to the picture? I mean, you stated it, but is there any moral reason why this would be true?
Can I respond, Mansa?
Yes, please.
You know, this should be treated as a kind of a twisted case of what is called the linear period, GLN cross GLN, inside GL2N. Dima?
Yes.
You know about this, Dima, I think, about this period. You have some work.
Yes, but what's the relation of linear period to symplectic parameter?
I thought it is a theorem due to Jacquet and Friedberg that representations of GL2N which have a linear period must be symplectic.
Mm-hmm.
I think
okay.
If you have a representation of GL2N which is generic with a linear period, then it must be symplectic.
I see.
And you know, one could also think of this as a twisted version of the Shalaika period, which is also symplectic.
Yes, I was trying to write it, the Shalaika model, yes.
I see, I see.
So it is either Shalaika could be also treated as a twisted version of this case.
I see. Thank you. So I have one more question. How do you construct distinguished representations in step 5?
So in order to perform step 5, so yeah, you need to know more about type theory. So I have said that any cuspidal representation can be described by compact induction. How can I say that? So this group J has a unique normal pro-P subgroup denoted J1, and the representation lambda is constructed in a very specific way, and it decomposes into two parts: lambda W tensor lambda T. So W is for the wild part and T is for the tame part, and this part is trivial on J1, and this part is remains irreducible when restricted to J1. So two completely different behaviors on J1. And in step 5, if you start with a tau self-dual simple character, you can, so it is non-trivial, but you can manage to construct. So first, I should say that such factorization of the type it exists, but it is not unique. It is not unique, and it is not even canonical. But it is possible to make the decomposition exists at least. And so, starting with such a simple character, you can manage to construct a wide part, lambda w, such that lambda w, its contragradient is isomorphic to lambda w twisted by tau. And you can also assume that lambda w is distinguished in the following sense. Om H intersects J, lambda w C is non-zero. And somehow, distinction for pi, distinction for the cuspidal representation, compact induction of lambda w tensor 2 reduces to distinction for the tame part. And the tame part behaves like a cuspidal representation of a finite GLN group. And distinction for cuspidal representations of finite groups, it is easier to deal with. And so this way, you can construct a family of distinguished representation as in step 5. So roughly speaking, the fact that the endoclass theta has been fixed amounts to saying that lambda w is fixed and you can vary the tame part lambda t.
Thank you. Are there any further questions?
Yes, I wanted to ask. I wrote it. Perhaps you can expand a bit, Vincent, about the use of type theory here.
Yes.
Because in the beginning, you.
Yes. I see what you mean. So I think this. This answers at least to part of your question. So this explains how in step 5 type theory is required. There is also another step where type theory is needed. It is in step 4. So again, it is a non-trivial step. It is a crucial step. We need to prove that. Where is my pen? So remind you that step 4. We have to prove that if pi is distinguished, then pi contains some tau self-dual simple character. And for this, you write, so as I said in the middle of my talk, you write pi as a compactly induced representation. You restrict it to H. Or if you prefer, you write this space, so which is assumed to be non-zero. It decomposes as a product over double cosets of Om J G intersect H lambda G C. And then, so you need to analyze. So this means that the space is not zero, so there is at least one G such that the contribution of this space is non-zero. But at this step, you know nothing about G. So you need you need to go further to get more information about such a G. And the idea is to restrict to the subgroup J1 I've just introduced before, so the propy part of J. And so suppose that this one is non-zero for some G. By restricting to J1, you get J1 G intersect H lambda, and there is only the wild part which contributes, because the tame part lambda t disappears because it is trivial on J1, and so this is non-zero. This is the idea, and then to go further, you need to know more about the theory of simple characters and how it is related to what I call the wild part lambda W. I just add one more thing. How do you prove this implication? You do not prove it directly by exhibiting some two self-dual simple character, but you prove it by verifying that the numerical condition A and B is satisfied. So meaning that 2n over the degree of theta has the same parity as R, and that alpha is a norm if and only if R is even. So you have to check a numerical condition from here by using this.
Thank you.
Hi, can I ask another thing? Can you say more about this connection that sounds important? The Endoclass is defined on the p-adic side, but you use the definition on the Langlands side. So how do we know it's the same thing?
How do we know it is the same thing? So well, first, I did not really explain what the Endoclass means on the p-adic side, but if you accept that it has been defined, the interpretation on the Galois side is due to Boeschel and Enyart.
Okay. So do you actually need to go through the inners of the Langlands correspondence, or?
Yes, because so for step 3, for step 3 and 4, I need the interpretation of the Endoclass on the p-adic side, but for step 2, I need the interpretation on the Galois side. So I really need the two interpretations.
So this relation is not like a formal thing. It's something. It's like a deep thing.
Yes, it is not. It is not formal. It is not formal at all.
Okay, thank you.
Are there any further questions? If not, let us thank the speaker again. We have no seminar next week, but we will have a talk by Fan Gao on December 16. So see you in 2 weeks, and you can use next week to watch on YouTube some videos that you missed, if you wish. Bye.
Thank you. Thank you again for the invitation.
Oh, thank you for the wonderful talk.
So how